folks, this is Physical Science Module 6 Study Guide. For your definitions, you want to learn sedimentary rock, which is rock formed when heat, pressure, and chemical reactions cement sediments that have filtered down and laid on the bottom of a body of water. They get cemented together. You want to learn E, plastic rock, rock with the properties of liquid and solid. So this kind of rock is solid when it's subjected to a sharp force, and it's generally liquidy at other times. This occurs in the mantle due to the temperature and pressure, and will make a similar non-Newtonian fluid in class, so you can kind of observe how that works. You want to learn fault. A fault is a boundary between sections of moving and stationary rock. So where two tectonic plates meet each other is a fault. And epicenter. So epicenter has to do with earthquakes. And epicenter is the point on the surface of the land directly over the focus of an earthquake. So when an earthquake occurs underground, the point at which it occurs is the focus. The point on top of the ground above the focus is called the epicenter of the earthquake. And generally the quake is most intense right there, and then it spreads out and becomes less intense. I don't know if any of you are old enough to remember, maybe 5 or 6 years ago we had a noticeable earthquake here where we live, and that's rare in our area, but I definitely remember it was exciting and scary. So if you've moved around and you've lived in the West, out in California, they're more common, earthquakes are more common there, and not very common here. I've felt two in my life, both weak compared to many other earthquakes, I guess. So number 2 says, scientists often separate the Earth into 5 distinct sections. Name those sections. This is a tricky question, right? Because we've been talking about the layers of the Earth, right? And there are kind of 5 layers, right? You have like crust, mantle, maybe like the layer within the mantle, the asthenosphere, that's plastic rock, and then the outer core and the inner core, and you're trying to get like 5 layers there. But in this question, he's really talking about the whole Earth and not just the layers of rock that we see. So what he's going for here is the atmosphere, right? Like troposphere, stratosphere, mesosphere, thermosphere, exosphere. So the atmosphere, the hydrosphere, right? All the water contained on the planet, the lithosphere, and the lithosphere is basically all the crust and the piece of mantle above the asthenosphere, and then the mantle, and then the core. And absolutely, if you said atmosphere, hydrosphere, crust, mantle, core, I would take that too. Because it seems really random that he goes for lithosphere instead of crust and mantle separately. I don't know. So of the 5 sections listed, which can we observe directly? Okay, so we can observe our atmosphere directly. We can observe our hydrosphere, most of it directly. Like we can't always observe the groundwater directly or the depths of the ocean, but most of the hydrosphere, oh no, not most, a lot of the hydrosphere, parts of the hydrosphere, and we can observe the crust directly. So yeah. Number 4, what 2 regions of the Earth does the MOHO, which is the Mohorovičić discontinuity, or the MOHO discontinuity, separate? So the MOHO is between the crust and the mantle. I'll pull this out again. Right. Between the crust, this brown part, and the mantle, this orange part, I basically have left a gap where the MOHO would be in here. There's no gap between them, but we see that seismic waves bend as they pass from the crust into the mantle, showing us that they're made of 2 different materials. And the point at which they bend, the boundary between the 2 different materials, is the MOHO discontinuity. And then what about the Gutenberg discontinuity? So the Gutenberg discontinuity, we also see a material shift where waves bend between the mantle and the outer core, and that's the Gutenberg discontinuity. Right, we know the mantle is made of silica and it is solid, and we know the outer core is iron and nickel, and it's molten or liquid, and so we see waves bending at this point, and so we call that the Gutenberg discontinuity. Let's see. I've crossed out my number 5. That's interesting. Number 6 on my paper. So I may have the first edition paper here. So if my questions seem a little different than yours, stick with me. There are at least some similarities. My number 6 says, what is the difference between the ways that igneous rock and sedimentary rock form? So igneous rock is molten rock, right, magma or lava, and then it cools and forms rock. So igneous rock is just cooled off, melted rock. Sedimentary rock forms when sediments sink down through the water, form layers, and then during heat and pressure, chemical reactions occur and form those particulates into solid rock. Number 7, what is unique about the rock and the mantle? So there's a layer of the mantle called the asthenosphere where the specific heat and pressure cause rock to be plastic rock and have the characteristics of solids when it's under sharp pressure and liquid at other times, although a very thick, slow-moving liquid. Number 8, what is the main thing scientists observe in order to learn about the makeup of the interior of the Earth? So seismic waves. The way that seismic waves, earthquake waves, bend and change speed when they change materials within the Earth. Even though we can't dig down and see what it's made of, we can predict it based on the way that seismic waves travel through different materials. Number 9, which is solid, the inner or outer core? So the inner core is solid, iron and nickel. The outer core is molten, iron and nickel. Why is the inner core solid when the outer core is liquid? Well, temperature is high enough to melt iron, but the pressure is so big that we have pressure freezing in the inner core. And so the high pressure causes it to be able to be a solid even at a high temperature. Number 10, where is the magnetic field of the Earth generated? So it's generated by the outer core flowing around the inner core. So in the core. Number 11, what causes the magnetic field of the Earth? Well, there are 2 theories. So the dynamo theory says that the flowing electricity in the outer core around the solid metallic inner core is basically like an electromagnet generating Earth's magnetic field. And then we have the rapid decay theory, which says that the electrical current in the core is a result of how the Earth was formed and will slow down and fade out over time due to resistance. Number 12 was to describe them, and I basically just did describe both of them. So we'll go on to 13. What makes the rapid decay theory more scientifically valid than the dynamo theory? Well, I can't find good evidence for the rapid decay theory personally. Dr. Weil says that it made a prediction about the electrical or the magnetic field of other planets. And so that would, if I could find actual evidence of that, that would be really confirming to a theory. If it's able to predict and then that prediction is confirmed, that really makes a theory stronger. But I'm not able to find that. Also, our field is decreasing, and so that is predicted by rapid decay. It's certainly allowed by dynamo as well. So the textbook says that Mars's field was predicted by the rapid decay theory and then shown to be present, whereas the dynamo theory would predict that Mars does not have a magnetic field. I can look into it again. I'm really not finding any information about rapid decay anywhere I look. Number 13, that was 13. Number 14, why is a catastrophe like Noah's flood an essential part of Earth's history if rapid decay is true? So the only way for magnetic field reversals, which we know have occurred, to occur with the rapid decay theory is for a global cataclysm, like a flood, a global flood. Whereas the dynamo theory has another mechanism for field reversals, which we know have occurred. 15. What two reasons make otherwise good scientists ignore rapid decay theory? Well, I tend to ignore it because I can't find peer-reviewed papers written about it. But many scientists hold a worldview that is not based on a faith in the God of the Bible, and so they would hold to an Earth that's much older than the 10,000 years or less that's required for rapid decay theory. So if you think the Earth is older than 10,000 years, you would not be interested in the rapid decay theory. Whereas if you hold to a literal view of Genesis, then you hold to a 10,000 year or younger Earth, you would see that the rapid decay theory would fit that worldview better. Number 16, why would life cease to exist without the Earth's magnetic field? Well, the magnetic field of the Earth deflects cosmic rays, which would kill us. So, very helpful. Yay, magnetic field. Number 17, what are the plates and tectonic plates? So the plates are islands of rock that float on the asthenosphere, that layer in the mantle that's plastic rock. So these big islands of rock can shift around because they're on top of the asthenosphere, which is plastic rock. So they can collide or shift past each other or even draw apart. Number 18, what happens when plates collide? Well, if they are colliding like this, earthquakes. If they collide like this, then folded mountains. If they collide like this, then fault block mountains. Just for a few examples. We can also get some volcanic action in boundary lines between plates or faults. Number 19, what is Pangea? Pangea is the idea that there was once a supercontinent of land where all the tectonic plates were together in one place. So pan means global, right? Like pandemic means a global disease spreading, right? Which it's 2020, pandemic. So Pangea just means one global continent. And then because the tectonic plates can move those spread out across the earth, there's lots of evidence for this in terms of fossils that are similar on like the east coast of South America and the west coast of Africa, where they would have been joined and now have spread apart. Lots of other evidences of this. This could be explained by a cataclysm like the flood, where the fountains of the deep burst and everything moved. It could have happened also very slowly. We see today the plates move very slowly, so it could have happened over a great many years as well, depending on kind of the worldview that you have and the age of the earth. Either a young earth or an old earth could have had a Pangea and then spread apart. Let's see, what causes earthquakes? Rock masses moving along a fault, right? Earthquakes. So rock masses moving, they're kind of stuck, they're under pressure, and then they slip. Earthquake. Briefly describe the elastic rebound theory of earthquakes. So one rock mass near a fault gets caught on another, and they just bend. Hopefully you can see my fingers. See, they can kind of bend and shift without actually sliding, and then all at once they'll slide. If the pressure builds up and becomes too great, they'll have to slide. Right, so eventually the moving mass will break free, and they rebound to their original shape, and that sends off a shock wave, an earthquake, seismic wave, right? Number 23, seismologist detects an earthquake that measures a 4 on the Richter scale, and later he detects another earthquake that measures an 8 on the Richter scale. How many times more energy does the second earthquake release compared to the first? Okay, so here's how you deal with the math involved with the Richter scale. So the Richter scale has a base 32, right? So when you're dealing with math, the base is the number, and then you have an exponent. So your base is always going to be 32, no matter what kind of earthquake it is. And then to find the exponent, to find how much more or less energy was involved with an earthquake, you just take the Richter scale value and find the difference between the two earthquakes. So for example, one of these earthquakes was an 8, the other was a 4. The difference between 8 and 4 is 4. Let's get a different marker. Will this one work? It does. Okay, so you just subtract 8 minus 4 is 4, so this is going to be my exponent. So I'm going to take base of 32 and raise it to the 4th power. Now remember, exponents don't just mean do 32 times 4. That's not what exponents mean. What it really means is 32 times 32 times 32 times 32. Right? 4 groups of 32 multiplied together. Right? So if you want to have a calculator on this test, that will save you some time. You can certainly do it that way if you want. So 32 to the 4th power means that, and if you multiply 32 times 32 times 32 times 32, you get 1,048,576 times more energy. So this number, 1,048,576 times stronger if you have an earthquake that measures 8 on the Richter scale than if it measures 4 on the Richter scale. So let me make up another problem to give you a little more practice with that. Alright, let's say, I think the DC earthquake from like maybe 6, 7, Matthew was really little, I might be almost 8, 9 years ago. I think it was a 6.4, that's just from my memory, on the Richter scale. And the earthquake that I felt like 18 years ago when I lived in Annapolis, that I think it was a 3.2 at the epicenter. I'm sure it was much weaker than a 3.2 where I was. So let's find the difference. So the 3.2 was like a little rumble, like a train going by. The 6.4 was like my walls were moving and it was really scary. So it felt very different. So if we want to find the energy difference between a 6.4 on the Richter scale and a 3.2, we'll subtract. So 4 minus 2 is 2, 6 minus 3 is 3, so the difference is 3.2. So then what I do is I put down my base of 32, and then I raise it to an exponent of 3.2. Now for that you would basically have to have a calculator. Hold on. Okay, I found my calculator. So if I want to do, I actually don't think you'll get a problem like this on the test. I think you'll have a whole number exponent, so you would be able to do it by hand, right? If it were 32 to the 3rd, it would be 32 times 32 times 32, which is about 33,000. It's like 32,700. And we know from the last problem, 32 to the 4th was like a million. Right, 1,048,000. So this one will be somewhere in between. But if you want to know how to do exponents like that on my calculator, maybe every calculator will be different, but I would type in my base of 32, and then this y to the x button right here, I'm going to push that, and then just type in my exponent of 3.2, and I'll get 65,536. Right, so 32 raised to the power of 3.2 is 65,536, meaning the DC earthquake was 65,000 times stronger than the smaller earthquake that I felt probably 18 years ago in Annapolis, which was a 3.2. So that's a quick lesson on exponents. Maybe I'll do one more that does whole numbers, since you won't have to worry about decimal ones. So let's say there was a terrible earthquake with a magnitude of 8, how much stronger would that be than, actually, we could do this kind of backward, hold on. Let me look at a problem. Okay, you don't actually have to do the math, kind of in the way I was worried. So, we can just say, if we had an earthquake that was an 8 on the Richter scale, how much stronger would that be than an earthquake, let's say that's even a 7 on the Richter scale, right? So we'd subtract, we'd get 1, that means 32 to the first power, so that just means 32, right? What if we said, we have an earthquake that is, let's say, 3 on the Richter scale, and we want to know how much stronger a 5 would be. So we would do 5 minus 3, they're 2 different, 32, raised to the second power. I would just type into my calculator 32 times 32, and I would find that to be, if they're just separated by 2 numbers on the Richter scale, then 1,024 times stronger for the 5 than for the 3. Let's see, so that's basically how the Richter scale works. It's a base 32, and then the difference in Richter scale numbers just becomes your exponent. Number 4, name 4 kinds of mountains and how do they each form. So volcanic mountains form when magma breaks through the surface and comes up and then piles up and forms a mountain. Domed mountains form when there's magma under the surface pushing up, and that just like causes pressure that makes the ground raise up and form a mountain, a domed mountain. A fault block mountain forms when 2 crusts with different densities collide, 2 tectonic plates, and at the fault, the denser crust goes under, the less dense crust goes above, and you get a fault block mountain. And then a folded mountain is like a head-on collision. 2 plates collide and buckle like this, and they form folded mountains. Pressures coming from both sides of equally dense or nearly equally dense plates. So that's your whole study guide.